Hello everyone. Today we will explore the mystery of the ghost particle or the neutrino. We will travel from its discovery in Italy to deep underground experiment to find out how this tiny particle change our understanding of the universe forever. Let's get started. In the early of 1930s, physicists were puzzled by beta decays. Energy seemed to be disappear into thin air. To preserve the fundamental law of physics, Wolfgang Pauli proposed a radical hypothesis. An invisible ghostly particle was carrying the energy away. The great Italian physicist Enrico Fermi gave this particle its name. In Italian, neutrino means little neutral one. It was a fitting name for a particle with no electric charge, and as it seemed at the time, no mass. From 1930 to 1950, detecting these particles was considered nearly impossible. Neutrinos interact only via the weak nuclear force, meaning they can pass through a box of lead at light year thick without hitting a single atom. To the scientists of the era, the neutrino was a ghost that refused to be caught. In the 1950s, Kai Cohen and Frederick Linus decided to hunt the ghost. Their mission was named Project Poltergeist. They utilized a process called inverse beta decay. When an anti-neutrino hits a proton in the tank of water, it creates two things, a neutron and a proton. The proton immediately finds an electron and annihilate, create a flash of light. The neutron is captured by cadmium chloride dissolved in the water, creating a second flash of light microseconds later. The experiment was conducted at the Savannah River plant in South Carolina. They placed their tank deep underground, right next to the one of the most powerful nuclear reactors. The reactor provides an incredible advantage. A massive concentrated flux of neutrino by being so close to a controlled nuclear source and sealed underground from cosmic rays. The researcher finally captured a neutrino hitting an atom. The ghost was real.
While humans were making neutrinos in reactors, the universe was already flooded with them. Deep inside stars, neutrinos are generated through nuclear fission. In the core of our suns, hydrogen atoms fuse into helium in a process called the proton-proton chain. During these reactions, massive amounts of energy and nearly trillions of neutrinos are released every second. These solar neutrinos fly straight out of our sun at nearly the speed of light, passing through the Earth and you as if we weren't even there. In the 1960s, Ray Davis and his colleagues set out to count these solar neutrinos. They built a massive tank filled with 100,000 gallons of perchloroethylene, or the common dry cleaning fluid, nearly a mile underground in the Homestead Gold Mine in South Dakota. The detection method. Occasionally, a solar neutrino would strike a chlorine-37 atom in the fluid, transforming it to a radioactive argon-37 atom. Davis would then sweep the tank every few weeks to count how many argon atoms were created. Davis' experiment worked, but it created a crisis. He found only one-third of the neutrinos that the standard solar models predicted should be there. This discrepancy became known as the solar neutrino problem. Scientists wonder, was the experiment wrong, or was our understanding of the sun or the neutrino itself fundamentally flawed? To solve the mystery, a new generation of experiments arose in Japan. The Kamiokande and later Super Kamiokande detector was a colossal tank of ultra-pure water buried deep in a mountain. When a neutrino travels through water faster than light, it creates a shockwave of blue light called Cherenkov radiation. It's like a sonic boom for light. Sensitive sensors lining the tank would pick up these faint blue rings. Researchers at Kamiokande discovered that neutrinos were oscillating. There isn't just one type of neutrino. There are three flavors: electron, muon, and tau. As they travel from the sun to the earth, They shift shapes between these flavors. Ray Davis experiment only look for one flavor, which is why two-thirds seem missing. This discovery of neutrino oscillation earned the Nobel Prize in Physics because it proves something revolutionary. Do neutrinos have mass? Yes. The supporting evidence is the discovery of the oscillation itself. According to the laws of quantum physics, a particle can only change its density or oscillate it if it experiences the passage of time. Since particles moving at the exact speed of light, like photons, do not experience time, a neutrino must be moving slightly slower than light. To move slower than light, it must have mass. Though their mass is incredibly tiny, millions of times lighter than an electron, it means that neutrinos are not just ghosts, but a tangible part of the fabric of our universe. Thank you.